this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're going to take a veering away from introductory astronomy significantly on this one when we talk about one of the most modern things that has occurred inside of the science of astronomy, as well as one of the most important things to happen in the last few years for all of physics and literally all of science. And it's the discovery of gravitational waves, or disturbances in space-time itself, due to the motions of extraordinarily violent collisions due to black holes. So I call this affectionately in one of my public talks, black holes and gravitational waves, the warp and woof of spacetime. If you don't know what the warp and woof of things are, you gotta go look that up. But it's also, there's, woof like a dog, is so it barks in the warping of spacetime, and warp and woof for you to go look at it. In any event, let's start off with a big explosion. So on September 14th of 2015, the LIGO Observatory received a signal of two colliding black holes that collided together 1.3 billion years ago. The two black holes were about 30 times the mass of the sun. One was a little bit larger than the other, and the stars around them that you see here as they merge together, the gravitational field of these two merging black holes formed an enormous wave in space-time. And as they waved, this is going to go in loop because I'm going to talk about it a bunch of times. So as they merged together, they formed a single black hole, and the stretching and warping of space-time released 3 or so solar masses worth of energy. What you see in here, the ring around the stars, is called an Einstein ring, and the light from all the stars is being bent by the extreme gravity around them. So really, that ring that you see around the two black holes, that single black hole at the end and the black holes at the beginning, is a result of stars directly behind the black hole with respect to our line of sight. And so it's not actually, the stars in the background aren't moving. That's just the path that the light takes to us from those distant stars so that we can see them. Now, this isn't actually what was seen. This was not the actual observation. This is a computer simulation showing what occurred if we were close by. If we were close by in space, there'd probably be a little bit crazier things happening there. That bending and stretching that you see there would be something that we would be part of, because that's the stretch of length and space and time itself. So it'd be it'd be like being inside a funhouse mirror and you're really being stretched and pulled. That would be kind of a violent place to be. So this is the gravitational lensing that you see there would also be something that's seen from every direction around them, but it's just our particular view from where it is. And so there's also the gravitational waves are being emitted, as you can see after it's done, the sloshing of the image as after they merge together. So during this collision, the power output in gravitational waves was far greater than the luminosity, all the light put out of all the stars in the entire observable universe put together. The collision of two black holes, which are only each about a couple of miles across, is actually the most powerful explosion that astronomers have ever seen aside from the universe's Big Bang. This detection was done by the LIGO Observatory on September 14th of 2015, and that signal was first seen, and eventually, after looking at it, was determined that one of the black holes was 36 times the mass of the sun, the other one was 29 times the mass of the sun, and the resulting black hole was only 62 times the mass of the sun, which suggests that the gravitational wave signal, that warping that you see, carried away 3 solar masses. So 3 solar masses was converted into wave energy propagating through space-time itself. And that is about 5 times 10 to the 47th joules of energy, if you really must think that. But really, it's just an enormous thing. All right, what's interesting though is that because they're waves that propagate outward from this black hole, you could actually think of them as having a frequency and a pitch. And in fact, their frequency and pitch is actually such that they would be audible in the human spectrum. So what we're seeing here is the actual pitch perspective of how fast it went, each of these two black holes went along as time went on, and you see that they, from left-hand side, you see the signal themselves, and the signal rises out of the background. And if you go check it out on the LIGO website, you see that it has a whoop 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 sound, which is really kind of fun. And this shows the actual appearance of the signal and how long it took to do the collision. So the simulation in the past was very, very, very wrong in terms of its time frame. The signal itself in that final collision took less than a tenth of a second. As a result of this discovery, and notice there's two indications, one from LIGO at Hanford, one from LIGO at Livingston, and you can see the frequencies in hertz are those of human audio, human ears. But they were really quiet. They were so very, very, very quiet, but yet they would have been audible had they been louder and closer. That's a weird thought. And so they're called chirps, because they go up at the end, like rip, like that. That's how they sound. They sound like rip as they come through. This discovery led to the Nobel Prize in Physics in 2017. So the LIGO Observatory, the LIGO, which is the Laser Interferometer Gravitational Wave Observatory, or LIGO, and involved over 1,000 people, roughly 1,200 researchers in about 20 countries. And this whole project took about 50 years from its first idea till the discovery. And the Nobel Prize laureates, which were each incredibly important to the creation of this, were Rainer Weiss, and the other half was to Barry Barish and Kip Thorne. And these three people were the main leaders in creating and developing the LIGO-Virgo collaboration, which observed the creation of the detector as well as the final observation of them. And so I provide that web link on the Nobel Prize for you to go look at. And this actually began kind of back in the 1970s, after Rainer Weiss did analyze some possible sources for background noises that could disturb measurements of gravitational waves. And so he had eventually designed a detector of some kind, and actually he presented it to Barry Barish and Kip Thorne, and Kip Thorne thought, well, I just wrote a big book on gravitation with Misner, Thorne, and Wheeler, which is one of the key books of general relativity. And in that book he said gravitational waves will never be observed because you can't make an instrument sensitive enough. Well, it's interesting to write the book that says it can't be done and then go out and do it, isn't it? That's exactly what Kip Thorne did. He became one of the most important people in it because he said, well, wait a second, that's what I wrote. So he, of course, added a chapter later on and revised his book. So this is a laser-based interferometer, and that could overcome the noise. And Kip Thorne and Rainer Weiss were early on convinced that it could be done, and so they pushed it through to one of the largest projects that's ever been funded by the National Science Foundation in the United States' history. So where did this come from? All right, why do we think there's gravitational waves? Well, the first thing we have to remember is that gravitational waves are a result of a new way of thinking about gravity. Gravity, as thought by Newton, was very different than we think about it today. Newton, and the key thing is that Newton's formulation of gravity says that the force due to gravity propagates instantaneously throughout the cosmos. It only depends on the masses of the two things gravitating and their distance. It has nothing to do with time in the force in his equations. However, the reformulation of gravity in terms of space-time meant that time itself was part of the equation, and so therefore disturbances or changes in the locations of masses or their distributions will cause changes in the gravitational field, and those changes propagate out at the speed of light. So what's the equivalence principle? And where did this all come from? The concept that Einstein had about the nature of gravity came about from the equivalence principle. He first developed the concept of special relativity in 1905 with the idea that all laws of physics are the same no matter how they move with respect to each other. No matter how they're moving, all laws of physics are the same. That means every law of physics, including quantum dynamics, electricity and magnetism, Galilean relativity, a Newtonian mechanics are all the same for what he called an inertial observer. An inertial observer is somebody that's inside a box, inside a reference frame, inside a room with lots of sticks to do measurements and clocks to do measurements of time. And that's how you do your measurements of time and space. And either you're in free fall, such as the description, such as the little cartoon in the lower left, or you're floating, and so you can't tell if you're floating, which is the lower left, or if you're in free fall, like the lower right, you still can't tell if you're floating in space or in free fall. They're the same thing. There's no way to tell whether or not they're the same thing. Or you could be moving at a uniform speed. Now, if you look in the upper right, that's not a uniform speed because the engines are on. So let's say you are floating in space and moving to the left really fast at half the speed of light or something like that. Or you're driving down the highway at about 80 miles an hour and there's no turns or twists, and maybe it's out in Wyoming or something like that where you can drive for 30 miles and you don't hit anything. So either you're moving with a uniform speed or you're in free fall. You can't tell if you're floating or standing still. Or you're falling in a uniform gravitational field. There's no way to tell any of these apart. So general relativity says you extend the concept of special relativity to include gravity as a fundamental interaction that's relative to the observer. And so Newtonian gravity said that there was a force between two masses that acts instantly. But now we can think of it instead as you're falling into the shape of space-time. So the reason the guy in the lower right is falling is because that's the shape of space-time. He follows the lay of space-time. So mass tells space-time how to curve, and then matter follows that curvature. That's what we mean by, that's what the end result of the equivalence principle is. In addition, where gravity then comes in is that in the up top two cartoons, we see a person standing on the Earth experiencing 1 g of gravity, which is 9.8 meters per second squared of acceleration downwards. Or you could be in a rocket out in space where the rockets are pushing you from below at 9.8 meters per second squared with a thrust, a force, due to the rocket engines at 9.8 meters per second squared. Now, of course, one person's on Earth and one person's in a rocket, but everything else, all other things being equal, will be equal, meaning every other experiment will be on a rocket will behave just as though you're dropping something off of a table. So if you had a table and push something off, it would fall downward and accelerate down to the ground, just as if you were on Earth. And if you were on Earth, and he threw something up in the air, it would fall back down. And that's exactly what would happen inside a rocket. So you can't tell the difference of any kind of acceleration. You can't tell the difference between the acceleration due to gravity and the acceleration due to any other force, such as a rocket or something like that, or being pulled up very rapidly by a cable. And that's what the equivalence principle says, is that not only are the physical laws the same no matter how you move with respect to each other, but it also says that you can't tell the difference between your inertial mass and your gravitational mass. They are the same thing. So Newton's mass that he derived from his laws of motion and his definition of inertia then becomes the thing that is inside of gravity itself. And so this concept of mass then is that mass affects space-time, and in fact warps it and changes its geometry such that other masses obey the geometric shape that has been put down by a bigger mass. So that's what the essentials of this equivalence principle are. And so when we think about what we mean by this move, we then say things gotta move, right? So how do you know if things move? Well, you need a meter stick or some sort of measuring tape or some way of measuring distance. And so that distance measurement is incredibly important. But you also have to, in order to say how things are moving, that says things have got to take time to get here from there. So time is an element too, and so speed and time are important. So when you integrate them all, you have to say, well, why do things fall? They follow the shortest possible path in space-time. That's what they do. And that shortest possible path, its length is called a metric. And the metric is the thing that combines space and time together such that you can say it has to take the shortest possible path in space and time, which is an interesting concept. So now we're going to get into the meat and bones. I talked about this in my general relativity lectures, but I'll give little tiny bits here because, you know, what the heck, here we go. In the upper right-hand area, we see the equation, which is the Schwarzschild metric for a weak gravitational field, such as around the edge of the sun or at the surface of the Earth. So the left-hand side of that little ds squared, is the path length in space-time squared, just like Pythagorean theorem. We take the square of one side and square the other side, and the hypotenuse, that's where that's really coming from in essence, is equal to, there's some factor that involves Newton's gravitational constant g and the mass m and the distance r and the speed of light squared, and you take that thing in parentheses and multiply it by the speed of light squared and multiply it by a length of time squared. So that's the time length that we're going. And then you do that same little thing, but instead of minusing it, you plus it, and you have little dr squared, which is height above. So we're assuming a spherical thing like an Earth, and how high we are above the Earth is dr. That's its altitude above the surface, or above the center of the mass, or that's a good way of talking about it. And the d omega squared, r squared, d omega squared is like left and right. But we're only worried about up and down for that metric. And that's the gravitational metric, or for a weak gravitational field, we are going up or down inside of a gravitational field. Now, we can reformulate. There are many ways you can actually make a metric and measure the length in space-time. It depends on the conditions. The metric at the top shows what it's like near something like the Earth or the Sun. But if you now take some two big black holes and smash them together, they're going to affect space-time in a very strange way. But very, very, very far away from those two black holes when they collide, that wave that happened will diminish as space-time, as they progress through space-time, because they spread out. So as the waves spread out through space, as they progress, as they travel away from the event that created them, they spread out and get weaker and weaker and weaker. In fact, they get so weak that they almost get to the point where they're just tiny bumps in front of flat space. So flat space, we get rid of the 1 minus gm on the top and the 1 plus 2 gm over r squared thing at the top, and we're left with almost the thing in the middle that I show, which is now a path length ds squared, and there's no effect on time from gravitational waves, but there is a stretching to the left and there is a stretching to the right as the waves travel up dz. So x is left and right, dy may be forward and backward, and z is up and down. So as the wave travels from the top to the bottom, it'll affect things going left and right and forward and back. And that's what those little h's stand for, is the tiny, tiny, tiny bumps and deviations that occur to flat space-time very far from a gravitational wave source. And so we can model, since it's a wave and it's periodic, we can approximate, we can take as our first guess that the little tiny h's will be functions of time, just like a sine wave. And so a sine wave is just a very simple water wave, or sine waves are just a way of, if a sine wave can be best thought of as just a simple oscillator that goes up and down, and as you watch it go back and forth in time, take a spring, like a weight at the end of a spring, and lift it up, and then traverse it, and then carry that spring as it's going up and down off to the right. Now, if you're smart, you do this in a dark room, and then what you do is you have a light. The bob at the end is a light, so it goes up and down, and as you walk this thing, there'll be a wave type pattern that goes up and down, and you'll see that, and what you see as it travels will be a sine wave. And that's described by the amplitude A times the sine, which is the sine of how fast the frequency of the wave W, times the time that it goes, and so as you move, minus z, which is a little bit off from where you started. So that's the phase angle difference of that. So that gives you some periodic variation in the lump of space-time. And by small, I mean really small. 1 part in, say, 10 to the 21st. There's very, very, very few things that we ever measure that are that small, because when we think of dollars and cents, we only think of like 1 penny, which is 1/100th, or 10 to the 1 part in 10 to the second. Even if we think of things like trillions of dollars, we're only thinking of 10 to the 12th. Like $1 out of a trillion is only 1 part out of 10 to the 12th. But this is 10 to the 21st, and that's getting really hard to measure what that really means. So it's tiny. It's extremely tiny is a good way of thinking about it. Another way to think about it is that the size of an atom is about 10 to the minus 10th meters. That's the size of an atom. And what would be 10 to the 11th meters? Well, that would be something extremely big. That would be 10 to the 11th, 10 to the 8th kilometers. 10 to the 8th kilometers is about a light second away. Well, it's about 1,000 light seconds away. So that is well past the moon. So we're talking this diameter of actually it would be much past the moon, be out past Mars. So 10 to the 8th kilometers, not 10 to the 5th. So it would be 1,000 times further out past to the orbit of Mars. So something compared the diameter of an atom compared to the distance to Mars. That's that's on the order of 10 to the 21st of a different size scale. So this is a tiny, tiny, tiny change. So we're not expecting to see a funhouse mirror far from the event. So how do they move? And this is even more math. I'm sorry, but you got to take it because it's your medicine today. And the upper right-hand corner, we're showing that little tiny, tiny, tiny equation which shows the bumps. So I made the equation really tiny. But we can take pieces of that equation, the right-hand side, and then we see this equation that we have at the top is called the geodesic equation. And that geodesic equation looks at variations in time, variations in space, and shows the product of their variation of time and space, and compared to the acceleration of these things. And that variation is called the geodesic, and it says how do things vary as things propagate through. What are some symmetries to the space-time? How will things move? So the geodesic equation, if you plug things in, will show you how things move given a metric. So that'll show you the shortest paths. So plugging this stuff into that equation gives you the shortest paths. But the changes that the metric shows are so incredibly tiny that there are literally almost no changes to the geodesic, meaning there are no path changes in terms of the coordinate changes. So it doesn't push things across coordinate lines. It stretches the sizes, but it doesn't change the coordinates of anything. It's kind of a weird thought, meaning that the changes are so incredibly tiny, you can't actually see it doesn't push it across the tick marks of a ruler. So at tick marks of a ruler, whatever's being pushed don't get pushed across those tick marks. So you can't measure the change with the coordinates. However, there is a distance change, because once you add up all of the tiny pieces of the change as time progresses, then there is a distance change across a very, very large section. So while there's no coordinate system change, there's an actual length change, because the coordinates themselves get stretched and pulled, meaning this is weird, meaning the ruler itself gets stretched and pulled and squished and pulled as things progress. So you can't tell that there is a change, but there is a length change. And so that length change is called the strain. And that length change, we're calling it the little bitty tiny delta length of t as a function of the real length, which is the average change. And that's proportional to that sine wave we thought. And so the last bit is called the strain, which is how far is the length being changed. And this is the thing that when people say what we're talking about, this is what, when they say, oh, it's this, when we're going to talk about it, oh, it got shifted by this much. This is what we mean. These are the equations that we had, is looking at the actual length changes or path length that was done. So even though there wasn't a coordinate change, the coordinates themselves, the meter sticks themselves get stretched. So you can't do this with just 1 meter stick. So you have to have something that can detect a change, a relative change in distance to on the order of 10 to the minus 21st. So that's kind of small, and that's equivalent to saying, so again, let's give another good analogy. If you look at one of the little hairs that from your head that might have fallen to your desk while you've been listening to this and nodding off, but your hair might have fallen to the desk, and the width of your hair, that's very small. But imagine comparing that to the distance to the nearest star, Proxima Centauri. The width of a human hair is about a tenth of a millimeter. The distance to Proxima Centauri is about 4 times 10 to the 13th kilometers, or 4 times 10 to the 16th meters, or 4 times 10 to the 19th millimeters. So this is an enormous change. And so if you could somehow measure something, if you could measure the accuracy of the distance between the Earth and the nearest star to the accuracy of the width of one human hair, you'd have done a pretty good job. So that's what was done. That's why they got the Nobel Prize, and that's why it took 50 years to do. So let's see how they did it. All right, so they have gravitational-wave observatories. These were built. They took a huge amount of funding and money, and they were by the National Science Foundation. And the 2 observatories that were built, each of them has 2 long rulers, and you compare and contrast the strain difference between the 2 of the rulers, and they change with time, and they change with time in a very peculiar way. And so what we're doing is each of the lengths of each of the arms of this interferometer, which are the long things that stretch away from the central building, those things are about 4 kilometers long. And so if the length that they're bouncing things off of, the length that they're measuring is 4 kilometers, then they have to measure something that's smaller than the width of a proton, which is 10 to the minus 18th meters. A proton is about 10 to the minus 15th meters, so we're looking at the shift of something that is being shifted only 1,000th of a proton. And so you have to build something pretty accurate to do. So what exactly are they looking for? They're looking for interference patterns in waves. So what do we mean by interference patterns? So you take 2 rocks and throw them into water like this, and you get waves rippling out on the surface of the water. And if we look closely at the places where where the 2 waves meet, they combine and get higher, and that is called a constructive interference. And that's where we see it brighter and higher because it's reflecting sunlight. And then between the waves at the dips, it looks darker because of destructive interference as the waves go flat. So the waves pass through each other. One is positive, they cancel each other out because the trough of one wave meets the peak of the other, and when that happens, they cancel each other out and they're flat. And that's called destructive interference. So we're going to look for, in some way, constructive and destructive interference as the waves pass by and change the lengths of these rulers that we've built in these 2 locations. So what kind of waves are we looking for? They're not water waves. They're really weird looking waves. These are the kind of waves that we're looking for. Notice they do have a sinusoidal variation, meaning they go fast when they're in the circular form, and they go out to the edge and they slow down. But there's 2 polarizations to these waves, and both of them are demonstrated here. One of them is called cross polarization, or X polarization, that's on the left, and the other is called plus polarization, or just plus polarization, on the right. And these waves are affecting test particles as they pass through. So these dots are like test particles that are being affected by a traveling gravitational wave. That wave is coming out of the screen towards you, and that's what's happening, or into the screen from you. So they're coming perpendicular to the screen as you're watching this video, and this is how the stretching occurs. So notice if you have a combination of these things, it stretches it in one direction and squishes it in the other. And if you and they're right, and each of these stretchings and squishings is right angles to each other, right? So since they're not like 45 degrees in either the plus or the cross, the squishings are perpendicular to each other. Now, I said this is like going into the screen or out of the screen, but let's look at it from the side and make it look really pretty. So this is what it would kind of look like if you could visualize a gravitational wave passing from, say, the from the upper right of this image all the way to the lower left. It's a very strange sort of tube-like, worm-like shape. So you can see that the squishing, look at any individual circle or squished ring, the wave propagates along the tube. And so these waves propagate in this manner. It's not that they get fatter and thinner. They're getting squished and stretched as they go. You can follow any individual one of the hoops, and it's behaving exactly like I showed you before, but they behave sequentially, and that's the wave-like behavior we're talking about. The speed of the propagation of that wave, we're slowing it down really massively, of course, because it propagates at the speed of light. So this is the propagation effect of gravity through space. So when any massive object or any object changes its position, well, it has to be super massive in order to make massive gravitational waves. But these and they move fast enough so that things can kind of rearrange with each other more quickly. But a very massive gravitational wave event, some sort of alteration in spacetime, will cause all of spacetime to do this as the waves propagate outward. And this is the method by which they propagate. Remember, we talked that Newton said that the force due to gravity, not a force anymore, but the shape of spacetime, the shape of the force due to gravity was Newton thought of only depended on the masses and the distance. However, Einstein said it took time for the change in gravity to affect something distant. So the concept of gravitational waves comes way back from Einstein's thinking, but he didn't think there was any way to ever measure it, or even if it was real. He just thought it was probably just, it wasn't real, that it was a coordinate thing, and it was just something that would be worked out. But it ended up being that, yes, there is an actual stretching and squishing, and length actually does change while the coordinates don't change. And what do we mean by coordinates again, that the coordinates are not changing? Notice how the hoops are not getting near, well, they're kind of getting stretched and squished along each other. But see the little lines that connect them to kind of demonstrate that's kind of this wormy pattern? You notice that there's not more worm pattern lines being inserted or created. They're the same number of worm lines. I'm just calling them worm lines. But they're the same number of lines, and those lines are the coordinates. So you can say that how many, on the far left-hand side, you say, well, how many coordinate, say, worm lines are there around? And I guess to my eye, I count 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 steps around. We can think of eight pegs connecting each ring to each oscillating ring. So you don't increase the total number of steps. The size of the steps themselves change, and that is the stretching and squishing of spacetime. So the geodesic itself is the measurement of the change of the metric, but because of the tininess of the change, this is not a change in coordinates because there's still 8 steps. It doesn't grow to be like 10 steps. See how the ring doesn't grow and there's all of a sudden 10 steps? No, it stays 8 steps around a ring, especially that end ring on the left. So that's what we meant by the coordinate system is staying the same, but the length is changing. So notice the stretching of the lines between them, how they're actually oscillating. That is definitively a change in length as the oscillations go and propagate through. All right, so that's the propagation of a wave and what their shape is. So how do you measure this thing? Well, you use what's called a laser interferometer. And a laser interferometer takes a laser source, it shines it at a half-silvered mirror, so half the laser can propagate through the half-silvered mirror, and the other half can get reflected. Then the wave of light goes down and bounces off of a very steady target that doesn't move, and then the two beams then come back together and then recombine after one passes through the mirror and the other passes along it. And then if a wave propagates through, then the actual length of the arms changes with time. And you can see that the arms are getting squished and stretched, and the waves then themselves are either in or out of phase. If they're in phase, they constructively interfere and make a little bright light, and if they're out of phase, they destructively interfere. So as the arms change, you get a flicker. And that flickering of the light that we saw in the original thing, that chirping, is what was seen. So it basically saw lots of background static. Maybe the light was just shimmering a little bit. And then all of a sudden it went whoop. And there were just like a really, really, really fast change where it vibrated very, very, very quickly. And the lengths of the two arms, one got shook really hard and the other one got shook in the other direction. So what's being measured then is a time difference in the paths, and that's how the length works. Is that even though the coordinate distance has not changed, since the path length has changed and light has the same speed, then there is a time difference, and that's why the waves can be in and out of phase, and then create the interference pattern that we see. So there's a laser beam. The thing in the middle is called a beam splitter, and when this interference pattern, it passes them together, and that's why this is called a laser interferometer, because we measure the interference pattern as something affects one of the arms of the interferometer. So again, the ability to do this was scaled up over the course of about 20 years to be able to measure the width of something that's 1,000, a shake that was only the 1,000th of the size of a proton. So how big is a proton? So what a bunch of wonderful people did is they created this was created by T-Pile at Caltech to show you the exact size of a proton and exactly how big the shake was. So now we're down by that blue thing, and that's a proton at 10 to the minus 17th meters. So the tiny shake was 4 times 10 to the minus 18th meters. This shake is so small that if the proton were a ball, you couldn't see. It would be like walking on the surface of the Earth. You can see the curvature of the Earth. The proton is so big compared to the size scale of the shaking or the movement due to it, that actually the wave would see a flat surface as it pushed it across. So this is an amazing, amazing concept, that there's the electron zipping around a hydrogen atom. And so the center of a hydrogen atom is a single proton down to below 10 to the minus 15th meters, 16th, 17th, and 18th meters. And as the gravitational wave passed through, that's the shake that it did, and that created the tiny, tiny whip that came back and forth. That's why it took 50 years, and that's why Kip Thorne didn't think you could actually see it, because this is a very tiny effect. It's extremely tiny. So let's see exactly what the places are that we're able to actually see this effect, these gravitational waves that did this. So there are currently only a few gravitational waves in existence in the world. And there's the LIGO group, which has 2 observatories, one in Hanford, Washington, the other in Livingston, Louisiana. There's the GEO 600 and the Virgo collaboration, which is now online. This was an old slide, which is in Southern Europe. And then there's the Kamioka gravitational wave detector, KAGRA, which is going to be coming online pretty soon. Should be online now. In fact, it is. And then there's one there's LIGO in India. The Indian government broke ground starting in 2016 to start beginning it. So there literally are only 4 active gravitational wave observatories today, with KAGRA coming online pretty soon. So you have these things, and that's what's detected it. They're very expensive to build. They're extraordinary. They take extraordinary technological achievement in order to do, and they take a dedicated funding source as well as governmental support. These cannot be done by private investors in any way. So this is your tax dollars discovering the fundamental aspects of the cosmos. That's really what's happening for U.S. citizens listening to this video. So let's look at some of the observatories. This is LIGO Livingston, and you can see the main facility in the middle and the two arms, one stretching to the north and one stretching to the west, and there's an access road there. They put this in Louisiana because they found a place where there's not a lot of people around. That was part of the goal, and they want to make sure nobody's going to come up to it and mess with it. Even still, they have in some public talks that they've saw that the Livingston detector, they've had to do some repairs because some people come on up there and they think, hey, that looks like something fun to shoot. So they've actually repaired some damage to the sides of it due to entertaining people that hit it with a shotgun. So that's actually been done. In any event, they now encase this whole thing in concrete, and there's a big moat around it, lots of high energy, lots of high fences with barbed wire, and so they got a lot of security there too, whatever. In any event, it has to be secure, and it has to be very, very far from where things are really happening. So Louisiana's got a bunch of alligators, and they take it offline whenever there's a hurricane. All right, so the other one is in some place that literally nobody goes to. This is in Hanford in eastern Washington. And this area of eastern Washington was a nuclear bomb test facility. So it's one of the most radioactive locations in the United States, other than the Trinity site and some radioactive dump zones near reactors. And so what we see is one of the chambers going off to the left, above, and one going to the right, one to the left and one above. And each of the lengths of these arms is about 4 kilometers, so these are perspective views, and those are incredibly long arms. The detectors are so incredibly sensitive, remember they have to be able to see the motion of a proton, that at LIGO Hanford, they're able to detect when the tumbleweeds hit the outside, because they actually have to go clean the tumbleweeds off of this thing, because it is the upper desert. So tumbleweeds will come and they'll hit the side of the thing, and when there's a big wind, lots of tumbleweeds hit, and they go, what the heck is that? And they get a signal, and it ends up that tumbleweeds have been hitting it. They also can detect when Jupiter is in the sky and when it's below the horizon. They can also detect when big trucks are driving on the highway about 10 miles away. And they can also detect when there's building demolition in a nearby city. So that's how sensitive they are. So they have to continuously model what they see as noise, because background noise can be something like clouds going overhead, or rain, or somebody walking into the facility and dropping their keys on their desk. It's really quite that sensitive. So when people go into these facilities, it's a quiet zone, and things got to be really clean. Can't be no hoarders in these places because you can't have things falling down. So it's a mess. There's very little mess in these environments, and when they do have that kind of mess, they try to eliminate all those messes. In any event, nothing falls, or at least try not to make things fall in there because it can cause a signal. And that's what I heard from many of the other researchers. There's amazing talks if you go to TED and look for them. So here's the inside of where the two beams meet. The laser beams meet is where the interferometer beams meet. You can see a tube on the right-hand side going down that goes out one arm, and a tube going up to the left, and that's the other arm. And in the center is where the beam splitter is, and where the detector and where the interferometric detector is. And here's a worker looking over one of the beams, one of the beam tubes as it goes out. And you can see that they try to keep it clean. They try to keep as many things as they can. And hair dropping on the floor is kind of important because you don't want your hair getting inside those tubes, because it has to be insanely clean inside the laser tubes. So these are 4-kilometer laser tubes that must be evacuated and made to a perfect vacuum, or at least as best as they can. So they try to keep them wildly clean, clean room clean, so there's no dust to reflect off of, in order to make fake interference patterns. So you have to go in with clean hands and make sure you have a mask on so you don't breathe stuff out and get moisture inside there as much as you can. And then when they evacuate it, they have to make sure the temperature and humidity is just right, and they check for dust particulates and so forth. So when they're actually installing these things, they have to, one of the biggest concern is cleanliness inside of the tubes themselves. Well, what's at the ends of the tubes? At the far ends of the tubes are these wonderful mirrors, because it's lasers. So the mirrors have to be really quite perfect. And so they have to be prepared in such a way that the mirrors are incredibly flat. The material out of which they're made is almost completely pure, so there's no imperfections in them as much as possible, in order to assure that the laser bounces correctly, as well as that there's no imperfections that lead to strange mass distributions or wagging of it because you don't want, you have to have a macroscopic thing, so the measurement of it has to be very accurate. You don't want it to be out of balance in any way. That includes its chemical composition as well as its surface as well. So once these things get installed, they kind of look like this, and this is just before sealing up the end of the chamber, at the very far end where the mass would be reflected off of. And so this will be inside its own chamber, and this chamber will then be the target of the laser, and it will be reflected off of this surface. And the mirrors are, well, the only way you can actually see this thing is because the light is being reflected off of at some glancing angle. And without that, these optical surfaces have to be nearly perfect in their surfaces as well as their chemical composition. So that's the only way you can actually see them, is that there's a side reflection. Otherwise, you wouldn't be able to look directly at the surface. But now once we look more carefully, we can say, well, how do they actually do what they're doing? And they call these mirrors test masses. So the test mass is the thing that they're seeing if it's moving away or towards. Now the arm is the length of the laser beam, and so the length of the laser beam goes from where the laser comes out of the beam splitter, and then hits this test mass, and the test mass reflects the laser back to the beam splitter. And what they've done is that there's multiple layers to the entire system. And in fact, there's 4 layers in a quad suspension system. And if you look at the little graphic that I have there, you can try this at home. Take 4 equal lengths of string and put like a little fob, say like a bunch of locks or something, like combination locks. So tie some combination locks together on a series of strings like this. And in fact, probably nothing that can swing. You don't want any other additional swinging. So you want something like maybe, I don't know, something that's not going to provide extra swings to them. Maybe billiard balls or something. Tape some string to these billiard balls, tape it down really hard, wrap it up tight, and then put them together. Now hang them in this way, and then shake your hand back and forth rapidly, just back and forth in a little quick motion. The bottom one will move almost not at all. These quad suspension systems are used in extremely, really expensive cars like Maybachs to give you these incredible rides that are very smooth. So the better your suspension system, the more independent motions where waves can be dampened, the better. So I invite you to kind of try this at home with 4 separate things and just shake it fast. Now, of course, if you move it slowly, the whole thing's going to, of course, move. But if you just give it a pulse at the top, left or right, or back and forth, but not up and down, but either to side, then the bottom one won't move at all because the others above it will take up the slack. And so each of these mirrors weighs about 40 kilograms. And at the top, they're held by silica glass fibers, and these fibers are the things that connect them. So these tiny, tiny thread-like, very strong fibers that don't transmit any more of the vibration through them. And so there's another look at what one of the test masses look like in the beam splitter chamber. All right. So once they do that, then they put it all together and they've split the beam and they've reflected off of it and look for the signals. Here's what the test signals look like. This was the actual timing and profile of the signals that they looked for and observed. So at the bottom was a frequency spectrum to show what the frequency of the wave was as a function of time at the 2 locations, Hanford and Livingston. And this was what was seen for the first gravitational detection. Now what we can see is that there is actually there's an observational frame, which is at the top, and then the bottom one is a simulation. The middle frame is numerical relativity, meaning you don't just want to do this, you want to know that you're actually going to get something done. So one of Kip Thorne's major contributions to this was to promote the theoretical understanding of how these gravitational waves would look. So if you collide this thing together and smash that thing together, smash two black holes together, maybe one's bigger than the other, maybe one's smaller than the other, maybe they have spins, maybe they have an elliptical orbit, etc., etc. And you make huge computer simulations, and that's called numerical relativity. And when you put them together and say, well, this is what it should look like, you make a whole bunch of waveforms, and you do that in advance, very far in advance. And then once you get a signal, you check it. You say, oh, it's like one of those signals. Or it's not like one of those signals. So tumbleweeds hitting the surface of it will not make this kind of signal. A plane flying overhead will not make a signal that looks like this. Only two colliding black holes made a signal like this. And the residual, which is the third frame down from the top, is the background noise they had to eliminate. So the background noise could be like planes, clouds, dust, somebody's cat meowing 10 miles away. It could be a lot of different things. And notice that the two waveforms, and here was the thing that convinced them, is that the two observations, the one in Hanford and the one in Livingston, were measured at almost exactly the same time. Almost exactly the same time. The difference between the measurements of Hanford and Livingston, Louisiana, was their light travel time between the two locations. So if you shone a laser from Hanford, Washington to Livingston, Louisiana, and you would say, how long does it take for light to get from there to there? That was the time delay that was seen between the two signals. So that's how they knew they came from the same exact source. And they noticed the chirp signal is nearly identical. In fact, it's for all practical intents identical. And both of them saw the same event, the same time frame, and everything. So that's how they knew that this was the same thing. Now, they made the observation in September, and I remember that Christmas time, I actually visited my family. My mother and father live in Brownsville, Texas, and one of the research groups is at Brownsville, Texas, University of Texas at Brownsville. So I went and visited a couple of people there who I know, Joe Romano and Matt Benquista, who were on faculty at UTB at the time. I think Joe's moved on, but I think Matt's still there. He might still be. I forgot. I didn't bother to check before saying this. But anyway, at the time, they were there, and I visited, and only 3 months prior, this gravitational wave signal had been detected, and they'd been running all sorts of simulations and checks, and they've been checking it like mad. They've been in the middle of their checks, and I went in and I said, hey, I think this gravitational wave stuff is really cool, and I want to give public talks on it. I've given a couple public talks. And they have a gravitational wave, because since they're part of the consortium, one of the many universities, and they were 2 out of the 1,200 people that are researching it, their public relations person overheard me from the hall and said, oh, I'll get you some stuff. And she went out and got me a whole stack of posters and cards and things, and they just smiled and looked and said, this is really cool. Yeah, it's pretty big. And they just talked about, normal stuff. They talk about physics and things that they did not they didn't tell me anything. That was a bummer. They didn't tell me anything. They knew I was talking about this. They knew I put in a crazy little proposal for Watt trying to look for him in New Jersey, but whatever. That's neither here nor there. Anyway, that was kind of fun, and there's my shout out to them and their tight-lippedness, because a lot of people had to be real tight-lipped because they didn't announce it till February. Anyway, so here's what this signal's source looked like if you were to simulate what the gravitational waves in space-time were to appear to be far from the black hole at the moment of the event that happened in September, that was observed on September 14th, 2015. And it's been slowed down about 40 times. Remember, this happened over the course of like a quarter of a second. And as it did so, like 3/4 of a second was its total time. And it took about a quarter of a second for it to actually occur. So you see that the waves propagate out through space, and they actually, the space itself gets pushed in these incredible wave formats. But once it's together, it rings down into that, and the gravitational waves ripple outward in space. Notice it does this double lobed feature. And so I went look at the early segments in the early part, you see one going each way, like 2 arms to this. And that gives kind of what they call a quadrupole shape to the ripples. and that's part of what's being seen by the two, and so that is an expected result for gravitational waves. All right. And the only reason we're looking at this two-dimensional view is because the universe is 3 dimensions and the gravitational waves propagate out in all directions. But what we're really looking for is it's really hard to visualize going in three dimensions. So we pretend that we're in a fictitious 4th dimensional space looking down on this, and the waves going up and down into the blue are that. So the compression and rarefaction are the waves themselves in space-time, in our space. All right, so if we really wanted to look at it from a alien 5th dimensional being sort of thing, where 4 dimension of space and 1 dimension of time, here we see the event here. This is a simulation showing the collision of the 2 black holes, and the surface is actually our universe viewed from some hyperdimensional, hypothetical, flat, high dimensional space in which our universe is embedded, so a 4th dimensional space. So our universe to them would look warped as a 2-dimensional sheet, because now we just remove 1/3 dimension just to make it easy to visualize. Otherwise, you have to have 3 eyes in order to see it. And around each one of the black holes, the space bends down into this crazy, crazy, crazy funnel shape. And that warps the space-time due to the black hole's enormous, enormous mass. Both of them, they have enormous mass, about 30 times the mass of the sun. And the various colors depict how time is flowing. All right, so we're going to come back to this. I hope it'll replay. I'm pretty sure I said rerun the image. I hope I did. But near the black hole, the colors depict the rate at which time flows. So as time flows normally, very good. Near the black hole, the waves in the green region, that's time flowing at a normal rate. In the yellow areas, time is slowed by 20 to 30%, and where it's red, time is almost stopped. So that's another way of looking at that, is that the flow of time is in that particular way. So the redder it is, the slower time is going. When we're looking at the nature of the arrows, those arrows depict the arrows depict how space is flowing. So when we think about the direction of the flow of space itself, we can think of exactly what the free fall rate of something is at that location. And the free fall rate at near where it's red is the arrows indicate that the rate of flow of space-time. And I described what that means in a different video when I talked about Andrew Hamilton's concept of a river of space-time, where we can think of the arrows as flowing towards mass. And so space can be thought of as flowing, and the bigger the arrow, the greater the flow of space-time. And so you can even see that space-time itself is being warped and changed, because as they orbit each other, space itself is being dragged around, and the arrows show the direction of the dragging around. And the waveform that is created by these two things, the simulated wave flow. So we have a numerical simulation that shows the wave pattern, and then we also have the numerical simulation that gives rise to the visualization as well. And the blue area on the outside shows the propagation of those things. So just before the 2 black holes collide, as they're merging, we slow down the rate of the movie rapidly, and we see that there's these enormous bucklings and shiftings of space-time. As space-time itself gets warped radically, some of the greatest warpage of space-time since the Big Bang, and in that warping, 3 times the mass of the sun is taken away from the black holes to create the waves that you see propagating outward. So we can think of that as the most incredible storm that's ever been seen. And it's more like a space-time storm, as the fabric of space and time, the warping. And now, as you heard, that space-time has sounds, the woof of space-time, as the warp and woof of space-time has an enormous storm, like a crack of a whip or a chirp as they go out. If you were close to this, you wouldn't survive. This close, you'd be dead. So again, the course was all about million ways to die, and this is an incredible really bizarre way of going. So one more time, seeing it get slower and slower, and the arrow of space-time flows faster and faster towards it, and time itself slows down, and the warping in the physical dimension of space gets now rebent in multiple ways, curved back upon itself, not just anti-gravitationally. See, up is like anti-gravitationally, and then away. So this is a strong stretch in terms of space and time as mass is converted into gravitational waves. All right, so what does that look like here? This is interesting. So as the gravitational wave passed through the Earth, this is a really funny little animation made by Dr. Hurd at Caltech at MIT in the LIGO lab. We see that the Earth actually gets stretched and squished. That's an extraordinarily exaggerated view, of course, because we know that the stretching and squishing was only about the size of 1,000th the size of a proton, so yeah, that's not it. However, if the Earth were much closer, that would occur. If the Earth were within less than a light year, this would be what would happen. So that's kind of a really wonderful thing to think, that some things that this close got affected in this way. I think that would cause a few earthquakes, a few maybe, yeah. It would also cause, your milk to fall off your table. Okay, so where did it happen in the sky? When the gravitational waves were detected, the funny thing is that because it's just two of them, they can only detect roughly where they are in the sky. And so because they were only detected by the two detectors, this is as best they got. These oval-like banana shapes are a result of the location of the timing between the two, Hanford and Livingston, as well as the most probable areas get brighter and brighter and greener and greener. So the inner circuit, the inner yellow line is where they're 10% confident where it is, and the purple line is they're 90% confident that it was inside that purple area. And so you can get tighter and tighter and tighter in and say, maybe that's it. So it could be from the Magellanic Cloud. Nobody knows. But it had to have been much, much further than that. Because where these things occurred is that because of the waveforms and how quiet they are, the measurement of the waveforms said that they were approximately 1.3 billion light years away. Because the gravitational waves travel at the speed of light, that's how far they go. So this was the first detection of gravitational waves by anybody in the entire history of the world, and it won them the Nobel Prize for this discovery, for two black holes that collided 1.3 billion years ago. And the light and the signal from it arrived here on September of 2015. Now, what we find is that there are more ways that gravitational waves can be made other than this. There are many ways gravitational waves can be made, and that's just one of them. Colliding black holes are one. And the most important thing about gravitational waves was discovered extremely recently, and that's coming up next time. See you soon.